nearly zoned out then, and started listening to Batman. Okay, so this is a really quick video. Really is quick actually. That second strand of differential equations, we've talked about connected rates, so that's that chain rule stuff. And now we're talking about forming differential equations, and in another video, solving them by what's called separation of variables. Now, I really love differential equations. This was one of the things that uh, you really start to get into at uni, and it was one of my favourite things, and a lot of people's favourite things if they really liked applied maths. What is a differential equation and what are they for? Well, differential equations is you just, you know, whenever you write dy by dx is 2x, and if you just started off this way, this is a differential equation because it contains a derivative and a function. It's an equation involving the derivative. Do you see? Um, but in reality, what differential equations are for is to save, obviously for the mathematical exercise, but in a real life, it's to save society, scientists, companies a hell of a lot of money when companies um, approach a mathematician, they're doing it because they want the mathematician to simulate a situation. Let's say, for example, that we wanted to release a rocket into space. Obviously, that's a billion pound project, a multi-million pound project, and you've only got really one attempt at that, haven't you? It's a destructible, if it goes wrong, it's a destructible object. So a mathematician would be approached, can you please model the expected behaviors that this rocket uh, would exhibit and build the parameters on what you think is most likely going to work. So if you just randomly uh, chucked a massive firework or a thruster on the bottom of a piece of metal and went go, it's really likely to just smash into the ground, isn't it? So mathematicians build a certain set of parameters. If you do this, it's most likely to work. If you do this, it's most likely to work. Your rocket will behave in this way under these conditions. And that's really, as differential equations get more and more advanced, that's what it's all about. That link between maths and physics. So for example, and this is what this section is, it really is a quick video. It's how do you begin to even construct a differential equation in the most basic sense. And then obviously as you go up in the levels, that modeling becomes more sophisticated and there are more things for you to consider and more variables to consider. But we're always really going to consider just two variables and constants, right? So you're going to get a bit of text like this. And how do we condense this text down into algebra? Well, this is where your highlighters come out or your underlining comes out, and you're looking for keywords, okay? So let's read this together. So it says, in the decay of radioactive particles, the rate at which particles decay is proportional to the number of particles remaining. Write down a differential equation to express the rate of change of the number of particles. That seems like a bit of a tongue twister, doesn't it? Seems like quite a lot of information and not really sure what to do with it. What you got to look for is triggers, okay? So we're talking about radioactive particles. So it would help if I defined a variable to mean particles. So I'm going to say let P be the particles, okay? It says rate. Now rate means rate of change. And as soon as you're hearing rate or rate of change, we're thinking gradient. Differential, aren't we? Differential. And it's saying the rate at which particles, which is P here, decay. So as soon as I hear rate, I'm thinking dP over, well, in this case it's going to be time, isn't it? They decay over time. So change in uh, particles over change in time. It says proportional to. So proportional is that little fish sign, okay? As soon as you hear proportional, fish sign. And it says decay. So decay means that the rate it's changing, it's decreasing, isn't it? So it's going to be a negative gradient. If you're looking at this on the graph, the population of a graph of the population, it's going down, it's decreasing, okay? And it says proportional to the number of particles remaining, so P. How do I translate this into an equation though? Because remember, an equation has equal signs in it, not fish signs. Well, proportional means, if I say 2 over 4, well, that's proportional to a half, isn't it? Do you see? 2 over 4 is some multiple of a half, right? Well, it's the same thing here. So dp over dt is proportional, so it's some multiple of p. It's parallel to p if we were talking about vectors, but we're not. So, in other words, whenever you see the fish, we're going to replace that with equals k, because it's some multiple of that thing, isn't it? The rate of change here is connected to the number within that population at the time. And that's it. Simple as that. That is your differential equation. You formed it. Let's try again. This time it says Newton's law of cooling states that the rate of loss. So, yes, hopefully we're getting this. We see that word rate, so I think it's something to do with a gradient function of loss. So again, we're thinking, oh, it's got to be a negative. Temperature of a body is proportional to the excess temperature of the body over its surroundings. This looks tricky. So Newton's law of cooling states that the rate of loss of temperature, so we're talking about temperature, is proportional to the excess temperature of the body over its surroundings. So if we say theta is temp of body, we're saying the rate of change of the body temperature is proportional to, it says loss, so minus. And now it's saying it's proportional to the excess temperature of the body over its surroundings. So if we say that the surrounding temperature is constant, and that's one deficiency of the model, because of course if I'm losing temperature, then the surrounding temperature is going to increase marginally, but such a small amount, probably very negligible if I was in a sports hall or something like that. So theta 0 is a constant in this case, and we'll call that surrounding temperature. Then surely the excess temperature is my temperature minus the temperature of the surroundings. But this isn't a differential equation yet. Remember, it's proportional, so I need an equals k on there. So equals k, but with a minus theta 0. And note here that for that to be applicable, k needs to be greater than 0, doesn't it? In order for that to be negative, because if k was less than 0, now my temperature is increasing. And just like before here, we're assuming that k is a positive constant. And that's it. That's it for form differential equations. So you're looking out for those keywords there. Rate means gradient. Loss or increase is going to be plus or minus. As soon as you see proportional, that's equals k. Put a fish sign first and then equals k. And then we can go from there.